Folks, this is dim and it has enormous mass. The fact that 3 indisputable pieces of evidence suggest something more. It's fascinating yet unsettling to think about. The immense vastness of space can be intimidating, and the mysteries that hide within it are even more so. One of the most captivating yet frightening subjects in space exploration has always been black holes. These cosmic giants have been the subject of intense research worldwide as scientists strive to understand what black holes really are and what lies within them. However, things have just changed. Neil deGrasse Tyson recently revealed something monumental. Our black hole is actually smaller than the one at the center of the Andromeda Galaxy, our nearest large galaxy. Yes, we may have a form of black hole envy. Finally, we may be on the verge of understanding what's inside a black hole. And trust me, the answer might just blow your mind. So, join us as we embark on this intergalactic journey and attempt to answer one of the most profound questions in science. What exactly is a black hole made of? A massive explosion causes the birth of a black hole. Its mass is compressed into an incredibly small region, creating such intense gravitational forces that nothing, no light, no matter, can escape. Once something crosses the event horizon, it is doomed to remain trapped forever. Black holes come in different sizes, ranging from stellar mass black holes that can be just a few times the mass of the Sun, to supermassive black holes found at the centers of galaxies, which can have millions or even billions of times the mass of our Sun. For many years, we've observed the effects of black holes indirectly, uncovering secrets little by little. Despite their immense size and strength, black holes do not simply exist, they are born. Their formation requires the remains of massive stars that have exhausted their nuclear fuel. These stars undergo a supernova explosion, a dramatic event marking the end of their life. In a supernova, the outer layers of the star are violently ejected into space while the core collapses under its own gravity. If the core's mass is several times that of our Sun, gravity overwhelms all other forces, causing it to collapse inward. The result is a black hole. The size of a black hole depends on its mass. Stellar black holes, the most commonly known type, have masses from a few times to several hundred times that of the Sun. At the heart of every black hole lies a singularity, a point of infinite density and curvature in spacetime. According to our current understanding of physics, the laws of nature break down in this region. This singularity is an area where our traditional theories of physics cannot fully explain what happens, leaving us in the dark about the true nature of black holes. To understand the singularity, we must think beyond our current physical laws. Singularities are not just theoretical. They appear both in the beginning of the universe, the Big Bang singularity, and at the center of black holes. As we look back at the Big Bang singularity, we encounter a crucial challenge. The universe is thought to have originated from an extremely hot and dense state about 13.8 billion years ago, but as we rewind time, the conditions of general relativity fail to explain what happened at that time. This breakdown suggests that our current understanding of physics cannot fully describe those early moments. To solve this, we need a theory that combines general relativity with quantum mechanics, quantum gravity. Quantum gravity seeks to unify the behavior of spacetime on both cosmic and subatomic scales. Such a theory could shed light on the nature of singularities and how the universe truly works. One potential approach to resolving the problem of singularities is loop quantum gravity. This theory suggests that, at extremely small scales, spacetime is quantized, meaning it consists of discrete, indivisible units, often referred to as loops or spin networks. In loop quantum gravity, the idea of quantization is applied to spacetime itself. This means spacetime is not considered a continuous, infinitely divisible entity but rather an interconnected network of discrete units that form the underlying structure of the universe. Within this framework, singularities, such as those in black holes and the Big Bang, could be avoided. According to this theory, as matter falls toward the singularity, the fabric of spacetime becomes more compressed, but it never reaches infinite density. Instead, the matter undergoes a quantum bounce near the center, reversing its collapse and causing it to expand again. This creates a new region of spacetime inside the black hole, often referred to as a quantum black hole or a bounce region. Stellar black holes, the most commonly observed type in the universe, form when a massive star collapses under its own gravity at the end of its life. When a massive star runs out of nuclear fuel, The outward pressure generated by nuclear reactions is no longer able to counteract the inward pull of gravity. As gravity takes over, the star collapses, leading to the formation of a stellar black hole. Nordstrom black holes depend on both mass and electric charge, whereas common black holes are charged and rotate. They are described by the Common solution in general relativity. The combination of electric charge and rotation leads to unique phenomena in these black holes, one of which is called frame dragging. This effect occurs because the rotating black hole twists and bends the surrounding spacetime. Common black holes have an event horizon as well as an inner boundary known as the Cauchy horizon. This boundary separates the region outside the black hole from the area where strange phenomena occur. The presence of an electric charge in a black hole creates a terrifying electrostatic force in addition to the gravitational force. This electrostatic charge can affect the behavior of nearby particles and matter. For example, charged particles may experience repulsion due to the black hole's electric charge, altering their trajectories and dynamics. Although charged black holes are theoretically possible, they are not expected to occur in nature. Most black holes are formed through astrophysical processes that result in neutral objects, meaning they lack a net electric charge. If a black hole were to acquire an electric charge, it would likely neutralize itself over time by attracting and trapping opposite charges from its environment. While we've learned much about black holes, observing one directly could transform our understanding of these enigmatic entities. As technology advances, scientists have finally managed to observe and confirm the existence of black holes. Not just one, but two significant observations have provided direct evidence. The first direct image of a black hole was captured in April 2019 by the Event Horizon Telescope collaboration, which took a picture of the supermassive black hole at the center of the galaxy M87, located about 55 million light-years from Earth. The image, showing a glowing ring of hot gas surrounding a dark central region, represents the event horizon of the black hole. This observation confirmed the existence of a supermassive black hole and provided visual evidence of the black hole's event horizon and its surrounding accretion disk. Further observations from gravitational wave observatories like LIGO and Virgo have detected ripples in spacetime caused by the impact and merger of black holes. The detection of gravitational waves in 2015 marked a significant breakthrough in cosmology, providing indirect evidence for the existence of black holes. These observations confirmed the presence of binary black hole systems, where two black holes orbit each other and eventually merge, producing powerful gravitational wave signals. Despite our progress in understanding black holes, there is still much we don't know about them. As we continue to explore these mysterious objects, new questions arise that challenge our current theories and push the boundaries of scientific investigation. One of the enduring mysteries surrounding black holes is Hawking radiation, proposed by physicist Stephen Hawking in 1974. Hawking radiation suggests that black holes are not entirely black, but instead emit radiation over time. This radiation is thought to be produced near the event horizon, where quantum effects cause particle-antiparticle pairs to form. One particle falls into the black hole, while the other escapes into space. If confirmed, this theory could have significant implications for our understanding of how black holes interact with their environment and eventually evaporate over incredibly long timescales. Another area of active research is the role of black holes in the formation of galaxies. Supermassive black holes, located at the centers of most galaxies, including our own Milky Way, are believed to play a crucial role in regulating star formation and the evolution of galaxies through processes like accretion and feedback. As material falls into the black hole, it releases vast amounts of energy, which influences the surrounding gas and dust, affecting the formation of new stars and the dynamics of cosmic structures over vast timescales. The study of black holes also intersects with fundamental questions in theoretical physics, such as the nature of information and the fate of matter that falls into a black hole. According to classical general relativity, the information about matter entering a black hole is lost forever, as it is seemingly destroyed at the singularity. This presents a major challenge to quantum mechanics, which dictates that information must be preserved. Recent advances in theoretical physics, such as the holographic principle and the firewall paradox, have attempted to reconcile these conflicting views. The holographic principle suggests that the information inside a black hole may be encoded on its event horizon in a lower dimensional structure, challenging our understanding of how space and information are interconnected. On the other hand, the firewall paradox proposes that the event horizon of a black hole may be surrounded by a firewall of high-energy particles, potentially resolving the information loss problem but raising new questions about the nature of spacetime near the black hole. Beyond theoretical physics, observational cosmology continues to provide new insights into the behavior and diversity of black holes across the universe. A black hole forms when a large amount of mass is compressed into an extremely small volume. Despite their immense mass, which can range from a few to several times that of the Sun, black holes are incredibly small, with diameters often only a few kilometers. This extreme density leads to the creation of an event horizon, the boundary beyond which nothing, not even light, can escape. The event horizon marks the point of no return, where the gravitational pull becomes so strong that anything crossing it is inevitably drawn into the black hole. In addition to stellar mass black holes, there are intermediate mass black holes, whose exact mass range is still under investigation by scientists. These black holes are generally thought to have masses ranging from thousands to millions of solar masses and are often found at the centers of galaxies, including our own Milky Way. Their immense gravitational influence significantly impacts the evolution of galaxies. The formation of supermassive black holes is an ongoing research topic, and while many theories exist, one common idea suggests that these black holes form by the growth of smaller ones. In this process, matter such as gas, dust, and stars accumulates around the black hole, forming a swirling disk known as an accretion disk. The black hole's strong gravity pulls material from the disk, causing it to spiral inward and eventually merge with the black hole over long periods. This continuous accretion allows the black hole to grow to a supermassive scale. As matter falls in, gravitational potential energy is released, producing some of the most powerful and brightest phenomena in the universe. Another interesting variety of black holes are charged black holes, which have an electric charge. There are two main types: Reissner-Nordström black holes and Kerr black holes. These black holes exhibit unique properties due to the interaction between their electric charge and other factors like rotation. Reissner-Nordström black holes are charged but non-rotating and follow the Reissner-Nordström solution in general relativity. While their gravitational fields are influenced by their charge, the general structure of these black holes is similar to that of uncharged black holes. They still possess an event horizon, although the size of the event horizon in a Reissner-Nordström black hole is affected by its electric charge.